So what we're doing today is we're getting a volume instead of an area. Okay, so this is called a volume of solids. Volume of solids of a revolution. So what we're going to just be taking an area, a nice simple area. Like let's say the area from 0 to 1 of square root of x, right? And we're going to rotate it about an axis. Okay. So I'm taking this particular area here from 0 to 1. So this area. And I'm going to rotate it around the x-axis. And it's going to become a three-dimensional solid. So I typically will draw the ghost. So the 180-degree ghost. And then I'll just be trying to draw, because I'm talking about a disk method here, I'm really trying to draw coins. So you can see that what I've created is a solid. I can look at it from the side and see I have a bunch of stacked coins, and that's why it's called the disk method. Right, because each coin is a disk. So a side view or a cross section, you'd see a single coin, a single disk, right? And you can see the width of the disk here, kind of. So some coins are solid, and some coins have a hole in them. Like when I was in China, I remember some of the coins had a hole. Some of the holes were square, too. So, but when it's a solid coin, when I look at the cross section and it's a solid coin, I'm doing the disk method. And when it's I look at the cross section and there's a hole in it, that's a washer. Like if you ever put together furniture from IKEA, right? They put those little discs with a hole in it when you're tightening a screw or a bolt to protect the wood, right? So I think all of us know what so this is a disc, right? Solid coin is a disc. And then if we saw one with a hole in it, right? That's a washer. So what's our key here is, and we're gonna develop this formula, is that whenever we do disk and washer method, we're going to be perpendicular to the axis of revolution. That initial rectangle will draw perpendicular to the axis of revolution. So disk method. Right? Draw rectangle perpendicular to the axis of revolution. Right? Draw 180-degree ghost. This is my terminology. Right? I want to see that thing rotated down, and then the solid. Try and visualize, draw the cross section. And decide disk or washer. Set up the integral, solve the integral. And this is actually both, right? This is disk and washer. I'm kind of doing both here, right? So, but the key thing is draw the rectangle. Okay, now when we draw the rectangle, I need a little asterisk here, right? When I say draw the rectangle, I'm going to have to figure out some things about the rectangle. So set up the integral is going to be the hard part here. I still want to think upper minus lower, and I want to think from the axis of revolution. So right minus left, or upper minus lower from the axis of revolution. So upper minus lower, or right minus left from the axis of revolution. And it gets pretty darn confusing really quick, okay? But if you can remember that piece we were talking about on Thursday, that's really essential to this setup.
What do you mean by from the axis?
So this particular axis is the x-axis, right? If you're looking at my picture now. So when I draw that rectangle, the upper is just the function and the lower is 0. So that's it. In this case, it's as simple as it can be, but it gets really complicated. So it's a note for a little bit later.
Okay.
Okay. So I want to develop the formula here, and you can see I'm getting a volume, and from my picture here, it's pretty easy to see that I have what shape stacked. What shape do I have stacked on top of each other?
Rectangles.
Oh, almost, because look at the side view. Remember, they're quarters, right?
Oh.
Oh.
A cone?
Okay, yeah, it is kind of like a cone, but it's easier to think of stacked circles, right?
Okay.
Okay, so how do I get, so my area, I'm sorry, my volume, my volume, I need 3 dimensions, right? I need 3 dimensions to get my volume. So one I'm going to get from the area of the circle, which is pi r squared, right? And look at r, right? So pi r squared is the area of the circle. What part is the height of the coin? In my picture, what part is the height of the coin?
Why?
Yes, the function. Exactly. So we're going to get this function from pi r squared delta x, right? So delta x is the thickness of the coin, right? And r is the height of the rectangle. And so when I do an infinite number of rectangles, right? So right now I'm saying, sorry, volume equals the sum of pi r squared delta x, right? And then when I do an infinite number of them, I'm going to get the integral from a to b of pi f. I can still keep it as pi r squared dx. And there is my disk method. So the volume is the integral from a to b of pi r squared dx, where r is the height of the rectangle. And so why am I not saying f there? Because it depends on what the situation is. The rectangle could be just the height of the function. The height of the rectangle could be the height of the function, or it could be something far more complicated. So I have to wait and see what the picture is going to tell me. And now, uh, so even if that's confusing to you, that's okay. Okay, you can. There's another picture in the book. I don't know if it will help, but you certainly can look at that. But if I think about the disk method, it's still a pi r squared, but then I have to cut out an inner circle, right? So for my washer, I get the integral from a to b of pi times capital R squared minus little r squared dx, or dy, right? Or dy, right? Depending on the way I've got it set up. Right? Remember, when I draw my rectangles, I'm going to decide if they're vertical, I'm integrating with respect to x. If they're horizontal, I'm integrating with respect to y. Let me let my dog in the room. Hold on, please. Come on, Lucy. Come on. Come on. Come on up. We're learning the disk method, washer method. Come on. Come on. Good girl. So the picture plays a pretty big part. So do include pictures when you're doing problems. I will show you a GeoGebra sketch today that will give you a nice picture if you're having trouble. Some students have trouble with the pictures. Calc 3 will be tough if these three-dimensional pictures are tough for you. There's a lot of 3D stuff in Calc 3. So, but you'll get better at it if you practice it.
Robert,
Yes,
I have a
Angel.
question
Yes.
for the disk method. You said R is the height of the rectangle.
Yeah.
So is it of one rectangle? Like if you go to the picture that you drew, is
Yeah.
it of one rectangle or?
Oh yeah, sorry. So draw my
Okay.
rectangle perpendicular, right? And then you can see that rectangle kind of happen inside the radius or inside that side view.
Okay. Okay.
Yeah, thank you. So let's do that first one, right? That's a classic. Let's do the first one here. And then we'll rotate it around a different axis and see what happens as well. Okay, so here we go. So we got our process. We're not sure about it yet, but you've got the directions written down. So we'll see how it goes, okay? And maybe we'll adjust as we move forward. So I'm looking at the same area I just drew, right, from 0 to 1. And I want it rotated around the x-axis. And I'm using the function y equals square root of x. And so since I know my rectangle has to be perpendicular to the axis of revolution, my rectangle has to be here, right? And remember, that's just one of the coins. It's actually only half of the coin, right? Because I'm going to rotate it around. And now look at that one coin there, right? You see that one coin. And remember, there's a whole bunch of them. I'm stacking them, right? So that one rectangle is giving me the width of the coin and the radius of the coin. In this particular case, it's nice and simple. I look at that cross section, right? I can see the delta x. I can see the radius. And in this case, I know that radius is square root of x. How are we doing? So this particular cross section is a solid, so I know I need the disk method. So all I need is pi r squared dx, right? So the integral from 0 to 1 of pi square root of x squared dx. Nice and simple. So just pi x dx. which is pi times x squared over 2, which is pi over 2. That's the volume. Pi over 2 units cubed, who cares? Let your science teachers take care of your units for you. Right, in physics, the units are going to be hideous.
Professor, is something like this going to be on the midterm?
Not this easy.
Oh no, not the problem, but like disk or washing.
Yes. Yeah, you'll have area between curves, disk method, and or washer method, shell method, arc length, and improper integral.
Can you give us an example of a hard problem?
Oh yeah, you got them. You got them on my midterms. They're all on the midterms. So yes, but let me work up to the difficult ones here today, Ash. Okay.
Okay.
Ash is going, well, if I can do the tough one, I can do them all. So we can quit. Let's do the same problem, but let's rotate it around the y-axis. Okay. Everyone okay to move on here? New problem? So I want to take that same area from 0 to 1 of square root of x, and I want to rotate it about the y-axis. So notice here that my rectangle is going to fit somewhere inside from right to left. So in this particular case, capital R is from the axis of revolution to the end of the rectangle, to the far end. So right minus left. Right will be the far end in this case. And little r, if you can see there's going to be a hole in this, if you can kind of picture that I'm rotating this around, right? It's going to be solid on the outside like a can of tuna fish, right? Open at the top, right? Do you see that? And the inside is like a water drain or a funnel, right? So my cross section is definitely looking like this, right? So my capital R is this distance out here, and the little r, right, is this distance here. How are we doing?
So would the disk and washer method just depend on where we draw the ghosts? Or...
Yeah, it's actually dependent upon the axis of revolution, right? So you're given an axis of revolution, and then yeah, the ghost is the 180 of it, right?
Okay.
Yep. So what is my outer radius here? What is capital R? How far is it from that y-axis to that end of that blue area?
1.
1. Yep. And how far is little r? Well, it's the square root of x, right? But when we're integrating in terms of delta y, we've got to solve for x. So if y equals square root of x, we know x equals y squared. When you're integrating in terms of y, it must be a function of y. So I solve for x, basically. So now this volume, which goes from C to D, which is also from 0 to 1. of pi times capital R squared minus little r squared dy. Let me give you a moment to catch up with me and make sure you're okay.
I have a question.
Yes, Charlie.
Is that rotating on the y-axis or
Yep.
on
Yep, y-axis, yep.
looks right? Okay.
So we've seen two simple cases so far. What do you think so far? What's going on in your minds?
I'm confused on this one.
Yep.
Yeah, because it looks like it's rotating on the horizontal because there's a one and you subtracted and it also looks like a washer thing.
It is a washer. This is a washer. You're right. Again, let me see if I can get a little bit of a better picture.
The equation you gave us, we can use that for both discs and washers?
Yes. Well, one is a solid, so pi r squared, and one is a hollow, so pi r squared minus little pi r squared. Right. So just a solid circle or a circle minus a circle.
Okay, thank you.
Yep. So Charlie, here's my original area, and there's me ghosting it around, right? And so now I'm ghosting it around all four ways, and you can see the base is that circle, the top is that circle, but then inside, you can see inside. It's hard to draw this. Inside, it's building up like an ice cream cone, right? Inside is building up like an ice cream cone, but on the outside it's solid the whole time, right? So outside it's like a tuna can, inside it's like a funnel. And again, where am I getting that axis of revolution from? It says y-axis, so I'm going around this way.
Okay, Professor, I got a question.
Yes, Josh?
Would the small r tend to be the equation? Like, in this case, the y equals square root of
It
x?
changes. That's the tough thing about this type of problem. It changes. You have to be able to draw a
Recognize
picture
it.
and decide. Yeah.
So what do you mean? What can it range from it being the equation to it being clear that it can be the small r?
You'll see. It could be the function. It could be a horizontal line. It could be the function minus a horizontal line. It could be a function plus a horizontal line. But we just gotta, just keep this right minus left, upper minus lower piece involved, and from the axis of revolution, and then as difficult as it can get, we'll be able to do them.
Right, thanks.
Yeah, absolutely. So let's do one where we have just a more difficult more difficult integral, right? A little bit more on my level of an integral. So let's do another one, and then we'll take a quick break, and then we'll do some tough ones, okay? So let's take the integral of cos of x. From 0 to pi over 4 about the x-axis. So we're going to get this volume, right? We're going to do a disk method here. So my axis of revolution is the x-axis, right? And so I'm going to draw my rectangle perpendicular to that x-axis. And it's pretty clear what the height of the rectangle here is, just cosine, right?
Do you mean pi over 2?
Pi over 4. Oh, you're right. Well, pi over 2. Yes, sorry, pi over 2. 90 degrees, right? Thank you. Wake up. Yeah, pi over 2 is better. I could have done pi over 4, but it's fine. So this particular solid, right, is going to get me this shape here. And clearly you see that it's a single coin, right? It's a bunch of stacked coins. I guess my picture is not that good. Let me go to GeoGebra real quick. Now GeoGebra will eat your RAM, okay? GeoGebra, it's like geometry and algebra together. GeoGebra.org. And I'm just in the magnifying glass in the search box. I'm going to type disk method. Now I've got to find one, and I have to remember which one does it well. Give me a second here. Yeah, this one's pretty good. This is by Vivian Lisi. And I'm putting in my cos of x. And my a value is 0. And I'm going to do, I'm hoping she'll take pi over 4, or pi over 2, sorry. It doesn't like the, yeah, here's the picture of it here, right? Nice. Look at it. I'm zooming in on this picture over here on the right, so you can see the whole cosine curve. You can see that rotation. And you can see that if I change the number of disks, right, you can see that volume getting pure, right? You see that? The volume's getting nice and smooth, right? Just like when we did with integrals with area. So there's all a little bunch of little drag things on here for you to experiment and to get a better understanding of what's going on, right? So play around with those for sure. All right, let's finish this integral. We got a pretty good idea of what this thing looks like. So we're doing the integral from 0 to pi over 2. That volume is pi times the integral of the cosine function squared dx. And there you go. So now I've got a volume of solid. I got a question from chapter 6 that moves us back to chapter 5-7 with trig powers, right? Good. Let's everybody solve this separately. Don't just copy me. Anybody get there? Almost. Charlie, got the same answer? Eleanor, here? Not yet? David, you get there?
Yes.
Nice.
Isn't sine of pi 0, not 1? Or
Sign of oh, thank you. Oh my God, Robert. Thank you. That's better. I knew it was looking wrong. Pi squared, right? Charlie. Did you get pi squared over 4? Did you get the same?
I got pi squared over 2. I don't know where I'm making a mistake, but I do.
When you put pi over 2 in, right?
That's pi squared over 4, right?
Yeah, pi squared over 4. Thank you, David. Nima, you find it? You find that half you were missing?
I'm looking at it.
And of course, these I can do on my calculator to make sure, right? What do I get for pi squared over 4 for decimal? Where's my calculator? I get about 2.4674, right? And then if I go to like Desmos, or I'm going to do it on my calculator on the test, but calculator is a little clunky, but you're going to be practicing with your calculator for this test. But I'm just going to do it on Desmos. It's so much quicker. So I go to functions, miscellaneous, integral from 0, oops, not O, 0 to pi divided by 2 of pi times cosine squared dx. And there it is, 2.4674. It's like instant. So much quicker on Desmos, but I showed you how to do it on your calculator. So if you forgot, you can always Google definite integrals on TI-84, whatever you have, right? Let's see, who's missing? 4, 8, 12, 16, 19, 18, missing 2 students? What? Who's missing? I've got to take a photo of attendance. If you want to turn your cameras off for a second, you can. Okay, I'm done. Thank you. If there was a lesson not to miss, it was today's lesson. All right, let's take a look at the same integral rotated around the y-axis, and then we'll take a break. Okay?
Professor, I have a question.
Yes.
Now, what's the thought process behind doing the x over 2 plus 1/4?
I divide and conquer when I see this fraction. So I'm doing that integral first. There's my x over 2. So I'm doing the integral of 1/2, which is just 1/2 x. And the other one, I get a 1/2. I get a 1/2 of cos of 2x, but I need a 2 inside, so I need another 2 outside to cancel. And there's that 1/4. So I'm doing all those steps. I'm skipping them all. And you've already seen it's not good when I skip steps, but you do what you want to do. But just make sure you got. So I have a couple of students here that are double checking me. You're not going to have anyone on the test. So do it at in the process that you're comfortable with, at the speed you're comfortable with. All right, same problem, same function anyway, but different axis of revolution, right? And then we're getting closer to the more difficult ones. So same problem. We're taking that cosine curve, right, from 0 to 1 on the y-axis and rotating it around the right from there. And we're going from where to 0 to pi over 2. So now we're rotating around the y-axis. Now this one's nice. This is a nice little curve here, right? You can see it's just a nice dome, right? Top of an igloo kind of thing, upside down bowl, right? My rectangle, and it's solid, right? You can see that it's solid. The solid area that I filled in on the right is being rotated around and filled in everywhere, right? So, but my right-hand rectangle now, oops. Let me just erase some of this stuff. That right-hand rectangle, the right-hand side of it, capital R, is coming from y equals cos of x. But remember, I'm doing this integral now in terms of y, because I'm doing a right minus left. So my volume has got to come from the integral from 0 to 1 of capital R squared dy. I need to solve my equation for x. So I use my inverse, and what do I get? X equals cos of y. Oh, sorry, arc cos of y, right? Oh, pi, or arc pi times that, right? So the volume is pi times the integral from 0 to 1 of arc squared cos of y dy. And this one we can't do. This one we don't know how to do. Thank God. It's too tough. Actually, I think we can do it, but I'm not going to make us do it. This would be by parts. And inside of the by parts is by parts. Don't do this one, please. This is ridiculous. So I think I could do it with y equals arc cos of y, and then of course du is negative 1 over square roots of 1 minus y squared, and then dv would be the integral of arc cos of dy, y dy, and that one I'd have to do by parts to get v. So pretty nasty. But we're going to stop there. We're going to take a little break, and we'll come back and we'll do a couple from the book. Okay? So it's 9:17. Let's meet back at 9:30. So again, I'd like mind tap 6.2, number 1 to 18, 1 to 17, I guess. And we're doing an example from the book here. This is number 9. So 6.2, number 9. I've got the line y equals x. I've got the curve y equals x squared. So I want the region bound between them, but I want to rotate it about, oops, about y equals 1. So I think on web design there's two. There's one in the x direction simple, one in the y direction simple, one in the x direction with a shift, and one in the y direction with a shift. So first of all, we want to graph these, right? And so clearly y equals x is simple. Y equals square root of x is simple. And we're already guessing we need this region here. We need this particular area rotated around our axis of revolution to get a volume. And our axis of revolution in this case is y equals 1. Oops. Oh. Come on, Robert. And that's our axis of revolution, right? Y equals 1. So nice in that I know the disc and washer are always perpendicular. So the way it really helps me to remember is that the shell method are parallels. So shells are parallels. And then the other methods are all perpendicular. So shell method, shells are parallels is what I remember. And then the other one I know is just going to be perpendicular. So I need my rectangle like this. And you see this one's a little bit complicated. Right, so when I'm doing a washer, this is a washer method. How do I know it's a washer and not a disc?
Because bounded by two equations or two functions.
Yeah, I like that thought. I think that works. If I look at the ghost, right? So rotated 180 degrees, I can see that inner piece is empty, right? Do you see that inner piece is empty? And the outer piece is that perfect ice cream cone kind of, right? So again, that outer piece is a perfect ice cream sideways, right? And the inside is a funnel, kind of, again. I know my pictures aren't ideal, but I think you get the idea. So washer. The real key is the rectangle in the area is not touching the axis of revolution. When the rectangle is touching the axis of revolution, I'm going to get a solid out of it. When it's not, I'm going to get an empty piece inside. So I'm going in terms of delta x, right? How's everybody doing on this piece so far? You okay with the washer? You okay with delta x? Thank you, Serrano. Angel, thank you. Michael, nice. So, but the key is from the axis of now I have to find my radius, right? I have to find my capital R and lowercase r, right? I have to find the big radius and the lower radius. And so it's strange, but it's always from the axis of revolution to the end of the rectangle. The further away is the capital R. So meaning this distance right here is going to be capital R, right? And I'm saying to the end of the rectangle, right? So from the axis of revolution to the end of the rectangle, upper minus lower. So what is upper?
So 1 minus.
Yep, and the lower is 1 minus, the function there is x, right? So 1 minus x. Now before I do the lowercase, I want to just share with you a way that I would get myself to see this a little bit better. But if I drew my rectangle right here, right, that rectangle is so small, right? Yes? That rectangle is so small there, it's really a height of 0. And what's 1 minus 0? Right? If I take my formula for capital R, what's 1 minus 0 is 1. And so my radius there is 1. My radius is 1 there. Remember, I'm rotating around that line. So I can see that I'm rotating that whole thing around a radius of 1. When I'm rotating this piece around, I'm sorry, mistake. Oh, I'm sorry. What's the x value there? What's the x value there? 0. Sorry, 1. 1 minus 1 is 0. So there's nothing being rotated, right? It's really, really tight to the rotation there. But down here, again, the x is 0. And when I put in 1 minus 0, I get 1. So my radius there is this long radius, right? I had them reversed. Sorry about that. I think that hopefully that's making a little sense.
I got a question.
Yes, Josh.
So essentially anywhere from the middle and up, or down in this case, it'd be x.
Yeah, so if you see the radius as 1 minus x, anytime you're picking an x value of the location of your rectangle, like right now, maybe my x value is 1/2, then you can see my radius, that outer radius is 1/2 there. I'm just trying to give the numerical people a chance to not have to think about the geometry, right? If I pick x as 1, it's pretty clear I'm here on my curve. Oops, I keep doing that. it's pretty clear I'm here on the curve, and look at the size of the rectangle there, right? It's 0. The height is 0 there, right? That's what I'm trying to get at. What about my lower rectangle? So the lower rectangle here is coming from this distance. Again, axis of revolution, that's not a very good curly bracket there, but, you know, that's better. So there's my lower rectangle, right? From the axis of revolution to the closest end of the rectangle. And so what is that distance? It's 1 minus square root of x. How are we doing here? From the axis of revolution, upper minus lower, right? So starting at the axis of revolution, then do your upper minus the lower. So upper, right? So capital R will always be from the axis of revolution to the furthest end of the rectangle. And which one of them might come first, but you've got to do upper minus lower, right? The rectangle could be above the axis of revolution, right? Well, both of those have to be squared. So I'll do that real quick. And then I can go into my formula, right? So the volume is pi times the integral from 0 to 1 of the larger radius squared minus the smaller radius squared with respect to x. How are we doing? This is a WebAssign problem. This is a book problem. I guess, you know, same setup, easy integral. And ours will be same setup, difficult integral. Not that you can't do it. I'm just mad that WebAssign, we spent all this time in Chapter 5 doing these integration methods, and then in Chapter 6 they don't do any of them. Doesn't make any sense to me. Why did I spend all that time with you in Chapter 5? So I see the ones will go away. I'll get x squared minus 3x plus 2 rad x dx. And so you don't need to be copying me here. You should just be doing this integral, right? See you later. Enjoy. I get pi over 6. Anybody get there yet? Let me know. Well, I can tell you, when I first learned this stuff, I hated it because I didn't quite understand it. But that's kind of what we do as humans. Unfortunately, we tend to be haters of things we don't get, or and most of the time mistakenly. And so what you got to do is you got to practice, and you got to, think about the process. Make it your own, right? Watch your favorite YouTube nerd. Read. Help each other. Ask for help. Right? All of that stuff. I tend to find myself, if I hate things after a long time, I decide I'm not going to do them anymore. Like, I don't bowl. I hate bowling. I refuse to bowl. No, I'll do something else. You all go bowling. But that could be a career, right? I mean, God, if you're a biologist and you're going to let Calc 2 stop you from being a biologist, that's a mistake, right? But if you're some kind of engineer and you hate math, I don't know. It's gonna be a tough road. Anyone get there? Eleanor, you get there? Same answer? That's good for you, but I'm just checking to see if I got it right. Good for you. David, you there? Nice. You okay? So, what do you think? Not bad once you get it set up, right? Do you agree with that? It's not bad once you get it set up. And then, like I said, WebAssign, everything's turning into polynomials. So, and the only thing we're going to do, Josh, good. You there? Nice. Ours are going to turn into sine squared, or ours are going to turn into by parts, like x times arc cosine of x. If you look at my old midterms, you'll see all of these types of problems. And so then here's the thing: is now I don't have to ask you to do a problem from 6 and a problem from 5. I can just ask you to do a problem from 6 that turns into a problem of 5, right? And you'll be fine. It's not that difficult. Don't believe the hype, even if the teacher is saying it.
Are you going to give us a hint on the exam which method you have
Yes,
to use?
exactly. I'm going to basically tell you the methods that you'll use. I'll say, I'll say, do this improper integral using tic-tac-toe and L'Hopital's rule. Something like that. All right, let's do another. Let's do one more. With one of these shifts. I tend not to put a shift in. I think one of mine did have a shift. I think my midterm last semester had a shift, but let's do one more, and then we can decide what to do next. So this is number 16, 6.2, number 16. So anything in my midterms that says disk or washer now you can do, right? So anything in the midterms that says disk and washer. By Wednesday you can do all of the midterms, okay? So 16, I've got the line x equals y squared, x equals 1, about x equals 1. Keep doing that, about x equals 1. Well, x equals y squared, if I do a quick solve for that for y, I get what y equals plus or minus square root of x. So I already know that I'm doing this guy, right? Here's y equals plus square root of x, right? And this is y equals minus square root of x. And so that whole red curve is x equals y squared, right? If I give you one that I think is hard to graph, this one is not hard to graph. I will just give you the picture. And I want that region cut off at this line, x equals 1, which happens to also be my axis of revolution. Right? So that blue line is my axis of revolution. So you can see that I'm going to be rotating this, right, this thing around here almost to get kind of that football shape or rugby ball shape. Right? Do you see it? Kind of looks like maybe it looks more like an almond than it does a rugby ball, but since it's a disk method, right? That's pretty clear. And you can also tell it's a disk because the rectangle is touching the axis of revolution everywhere that rectangle would be. And so all I need is a capital R here, right? And it's from the axis of revolution to the end of the rectangle. And in this case, it's a right minus left. So capital R is 1 minus y squared, right? So since I'm doing this in terms of y, so make sure you're with me there.
I'm confused about when in the beginning you said we need to draw the rectangles like from right to left or from top to bottom with respect to the axis. And on the last one, where the axis was above the rectangle, you had flipped the upper and the lower?
Yes, because so remember, when I'm calculating the height of the rectangle, I always have to get a positive number. So if my axis of revolution is above, that's now my upper. Upper minus lower, right? To keep it a positive number.
Okay, but so would we ever have to flip the right and the left?
Yes, the same way, but I know what you're confusing. So I draw my rectangle perpendicular to the axis of revolution. Stop. Okay. And then I decide, am I in terms of x or y, right? Okay, got that now. Now I'm trying to calculate the radius. And when I'm calculating that radius, I always want to do right minus left or upper minus lower to keep things positive. And it's always from the axis of revolution to the end of the rectangle. So for example, if my rectangle was here and my axis of revolution was here, capital R would be x2 minus x1.
Oh.
It's always right minus left from the axis of revolution to the furthest end of the rectangle for capital R. So even though I'm going from here to here, I still want to get a positive, so I have to do right minus left.
Okay.
It's strange. All right, so I'm ready for my volume. It's pi times the integral from what, minus 1 to 1, right? If you think about it, remember I'm doing that whole piece, right, down from the lower part to the upper part, right? I'm moving this whole area around. Sorry, green. I'm moving this whole area around, right, to get that almond shape. And my radius is 1 minus y squared, but I need that squared, dy. Now there's some symmetry here, right? So I certainly can do this as 2 pi times the integral from 0 to 1 of 1 minus y squared, all quantity squared dy, because of the symmetry. right? Top and bottom are symmetrical. So I don't have to do the whole interval. I can do twice half of the interval. So now we're racing basically. And you can see the benefit of doing twice the integral from 0 to 1. When I plug in 0, they all go away.